Hello, AP Calc AB. We are moving into actually taking antiderivatives. So this is going to work with integrals. Basically, this is going to allow us to find the area under a curve. But for right now, we're just going to be pretty basic about it and just introduce integrals basically in a way of just calling it anti-differentiation. So we're backwards differentiating. So this is the other big part of calc, right? So we know how to take derivatives very well. We've been doing that for a long time. Now we're just working backwards with integrating, aka anti-differentiation. So I'm going to give you the calc notes, which consist of one line. Then we're going to get right into some examples. So a function capital F is a lot of times called the antiderivative of lowercase f, so long that when you take the derivative of capital F, it gives you lowercase f. This is just notation. This is just saying that, hey, if I were to, take the antiderivative, right, it's capital F. So if I were to go backwards, it's capital F. All right, so let's take the general antiderivative for each function. Let's get into some examples. All right, let's think about what did we have to take the derivative of in order to get a derivative of sine, right? So like what was our original function that when we took its derivative, we got sine? Well, okay, it's some sort of cosine, but if we take the derivative of cosine, we get negative sine. So our original function had to have been negative cosine of x. Now, we can always check this to make sure that this works, right? If we take the derivative of negative cosine, we'll get positive sine. Now, what if we had like plus 3 here in our original function? Just throwing out a 3, don't have to write it down yet. Well, if I were to take the derivative of this, I'd get sine. That's it, plus nothing, right? The derivative of a constant is nothing. Well, so that means that 3 could have been, a plus 17. It could have been a minus 20. It could have been any constant out there. And so what we do instead is we add plus c to show that it could have been any constant. So our function, negative cosine x plus c, if we were to take its derivative, we'd get this. That is what taking an antiderivative is. General meaning we have to have that plus c there because we don't ever know if there was a constant in the original function, because once you took the derivative of that constant, it was gone. Let's take a look at B. What did we have to take the derivative of to get 1 over x? Well, this was a special case, and that case was natural log of x. Now, we can only take the natural log of positive values, so when we take the antiderivative, we have to make sure that we put x in absolute value. And of course, our plus c. So, if we were to take the derivative of this, right, the derivative of the natural log of x is 1 over x. Great. The derivative of any constant, not there. So that's why general antiderivative has plus c for a constant. All right, part C. Okay, this one is a little tricky, right? We have to have had some function that when we took its derivative, we ended up with an x cubed. Okay, so I know that it had to have been an x to the 4th, right? Because we know that with a power rule, when we take the derivative of x to the 4th, we'll get 4x cubed. Okay, well, I don't want that 4 to end up there. I don't have a 4 out front here when I take the derivative. So how do I get rid of a 4? I multiply by 1/4. Let's test this out. And then, of course, my plus c. Let's test this out to make sure it works. How do I test out to make sure my antiderivative was done correctly? I take the derivative. Let's take the derivative of this. if we were to take the derivative of this, that I have to use the power rule. So I'd take the 4, multiply it by the 1/4 out front. Oh, 4 times 1/4 is just 1. Then I take 1 less in my exponent. So it's x cubed. So that does work. If I were to take the derivative of any constant, it's 0. So we can see that we're left with the derivative here. So that's how you take an antiderivative just in general. That's your thought process. We're going to do a couple more examples next. Okay, the general antiderivative for x to the n, so long as n is not -1. Let's think about why n can't be -1 here. What would it mean if n was -1? Well, that means x to the -1, which is 1 over x. We already saw that the antiderivative for 1 over x is the natural log of the absolute value of x. So this is going to be our general rule for x to the n. N can be any other integer, well, n can be anything except for -1. All right. So we just did an example of this, right? We just did on the previous page. We said, hey, if f of x was x cubed, then the antiderivative had to have been 1/4 x to the 4th. Okay, let's take a look at why that works again. If I were to take the derivative of this to test if I did the correct antiderivative, I'd take the 4 out front. 4 times 1/4, it goes away. X cubed. Boom. Of course, we need that plus c. Well, let's see what we did here. In this case, our n was 3, right? So for this particular example, we first added 1 to get what our exponent would be in our antiderivative. Great. What did we also do out front? We also divided by that n plus 1. So for any general antiderivative for this here would be, we added 1 to the exponent, so it's x to the n plus 1, but we also divided by that n plus 1 value. And then, of course, we added c. Let's do an example. Let's find the antiderivative of something x squared here. Let's do 4x squared. All right, so let's find that general antiderivative using our general form here. So what was n? N here is 2. So I'm going to have an x to the 3rd because I have to add 1 on. I'm going to keep this 4 out front. Nothing says we have to change that 4. But then I have to divide by the n plus 1. Well, since our n was 2, I have to divide by the 3. So if we started off with this f of x, its antiderivative is 4/3 x cubed. Let's make sure that works. Take the derivative mentally of this. You would take the 3 down using the power rule. 3 times 4/3, the 3 cancels, so you're left with 4x squared. You take 1 less. Of course, we need our plus c here to account for any potential constants that were in that original function, such that when you took the derivative of it, it went away. Okay, we have a few more examples using this basic rule. It's kind of like the antiderivative power rule. It's like going backwards. All right, here's a slide with the most common functions and their antiderivative. So this is just an extended table on the screen. This is the first part of the table here, and then it extends over here. So we have each original function written in blue, and then its corresponding antiderivative in orange. So if you have a constant out in front, it does not really affect what you're doing to your antiderivative, coefficient. That coefficient's going to remain out in front. If you're taking the antiderivative of two things added together, you take the antiderivative of each separately. Like the two examples we just did. I focused on each term separately. This is one that we discussed in depth on the other page. Anytime you have x to the n, so long as n is not -1, then you kind of do the backwards power rule right here. If n was -1 and you have x to the negative first, aka 1 over x, that antiderivative is the natural log of the absolute value of x. E to the x, because it's its own derivative, it's also its own antiderivative. We can work backwards with sine and cosine. You just need to be careful about your positives and negatives, right? The antiderivative of sine is negative cosine, whereas the antiderivative of cosine is positive sine. That's because if you take the derivative of sine, you get cosine. If you take the derivative of cosine, you get negative sine. So that means if you take the derivative of negative cosine, you get sine. These are other common ones, right? The derivative of tangent is secant squared. So if we started with secant squared, its antiderivative would be tangent. The derivative of secant is secant tangent, so vice versa. These were some of the inverse trig. These are the two most common ones. These are the ones that you should know. So the derivative of sine inverse or arcsine is right here. Therefore, the antiderivative of this is sine inverse. Same idea with tan inverse or arctan. Now, yes, should we have a plus c after everything in the antiderivative column? Yes. Yes, we should. I didn't put it here just for lack of space, but anytime you take an antiderivative, you should have a plus c. We will get into definite integrals later on in this unit, and then we won't need the plus c. But anytime you're asked to take a general antiderivative, you do need that plus c. So I would recommend getting these written down in your binder, and they're good to reference when you are working on antiderivatives. Okay, let's try a couple of these, finding a general antiderivative. Okay, in our first example, to find the antiderivative, which we'll call capital F, I'm going to keep my 6. I know that we're going to have to raise x to 1 higher than 3, and we also have to divide by that number. Again, make sure that that works. So if you took the derivative of what I'm circling here, you should get 6x cubed. Take the derivative using the power rule. You bring the 4 out front, the 4's cancel, you're left with 6x to the 3rd. Cool. Yes, we'll simplify this in the next line. Okay, next, we're going to do the same thing. Just because 2/3 is a fraction doesn't mean it follows any other rule. You know, we still can add 1 to it and divide. It's all good. You just need to be patient with your algebra. So we're going to have an 8. Okay, now what we have to do is figure out what plus 1 is here. So 2/3 plus 1. 2/3 plus 3/3 is 5/3. So we added 1 in the form of 3/3. And then we also have to divide by that 5/3, right? Yes, we have complex fractions. Yes, we'll deal with them in the next line. Okay. Oh, plus c at the end. All right. So our big f of x, simplifying 6/4 will give us 3/2 x to the 4th. Great. Plus, all right, I'm going to do this in a different color so you can just see what I'm doing here. So I'm going to take this and just work on it down here. Now I'm dividing by 5/3. What does dividing by a fraction mean? It means multiplying by the reciprocal of that fraction. 8 divided by 5/3 is 8 times 3/5. So that gives us 24/5 when we multiply through. We couldn't cross cancel at all. 8 and 5 can't cancel. 1 and 3 can't cancel. So we are left with 24/5 x to the 5/3 plus c. Again, how do you check your work? You take the derivative of this and make sure you get back to here. That would make sense, right? We're taking an antiderivative, so how do you check you did that correctly? Well, you work backwards. You take the derivative. Make sure that you get back to here. Again, we need the plus c. It's accounting for any potential constant that could have been on the original function that once we took the derivative disappeared. All right, let's take a look at the next example. So we want to take the antiderivative, which a lot of times we call capital F. All right, we got to think. This one doesn't have any variables in it, but just think about what did we take the derivative of in order to get 2/5, right? What was our original function that when we took the derivative, we got 2/5? 2/5 x. So if you take the derivative of 2/5 x, you get 2/5. It's just the coefficient out in front. Okay, next, we can take a look at this next function, and I'm going to rewrite it in a slightly different way off to the side. So I'm just going to look at this, and you could rewrite this as 2 times 1 over x, right? It's 2 1 over x's, it's 2 over x. We know that the general antiderivative for 1 over x, or x to the negative first, is the natural log of the absolute value of x. That was something we established on the first page. This cannot be used using the backwards power rule that we've been using over here. We can't do that because n is -1 here. It's 1 over x. So we will have plus 2 natural log of the absolute value of x plus c. Great. Again, you can check your answer by taking the derivative of this. The derivative of 2/5 x is 2/5. The derivative of 2 ln of x is 2 times 1 over x, or 2 over x. The derivative of this potential constant here, nothing. All right, these last two slides are figuring out what that c value is with some extra info. So this is written just slightly differently. We want to find original function f, and we're given its derivative. We're given the derivative, so we have to take the antiderivative, basically. Well, the antiderivative of this would just be f. So let's use our rules here. Okay, what is the antiderivative of 1? So what did we take the derivative of to get 1 as a derivative? 1x, right? The derivative of x would just be 1. Then what I would recommend doing is for the square root here, thinking of this as 3x to the 1/2 instead. That allows us to see it as x to the n. And our rule for x to the n was this, right? If you are taking the antiderivative of x to the n, it's 1 over n plus 1, x to the n plus 1. All right, so let's use that rule. N here is half. So we have to take x to the n plus 1. Okay, so 1/2 plus 1 is 3/2. And then we're dividing by that 3/2 as well here. And then we have plus c. All right. Then we have to simplify that complex fraction and also find c. All right, so this is really 3. So I'm going to do this off to the side again. This is really 3 times 2/3, right? We're dividing fractions means multiplying by the reciprocal of what you're dividing by. So 3 and 3 can cancel when we do that, so we'll be left with 2. If you didn't cancel, you'd be left with 6 over 3, which is 2. All right, so plus 2 x to the 3/2 plus c. Now, here's where we can find the c. We want to find the particular function that f is. This is the general antiderivative of f prime. plus C is general, right? It's not being very specific on telling us what C is. So we are going to use this information to find C. How do we do that? Well, let's take that info. This is telling us that if we were to plug in 4 for x, we'd get an output of 25. Okay, so here's our output, f of x. Here's our inputs. I need to input 4 and get an output of 25. So I can write that 25 equals 4 plus 2 times 4 to the 3/2 plus c. And then I can solve for c. Yes, this is a harder algebraic problem. That's why I picked it. Okay, let's figure out what this is. Right, so again, I'm going to do something off to the side. General pre-calculus stuff. So 4 to the 3/2, right? Anything to the 3/2 means, anything to the something over 2, this means square root. So this is the square root of 4. That's what this 1/2 is. And then it's cubed. Okay. This means that we can either take the square root of 4 first, right? We could write it like this. The 3 can go in either spot. So in this case, we could do it either way. I'd rather take the square root of 4 first and then cube it. But you could also cube 4 first and then take the square root because 4 is a nice number for either order. So if we do it this way, the square root of 4 is 2, cubed is 8. You also have your calculators with you. I don't know if you're using them or not. You can literally plug in 4 to the 3/2 power and you will get 8. Okay. So let's keep solving. All right, then we want to just solve for c. So if we combine 4 and 16 here, we'll get 20. And if we subtract 20 from both sides, we see that c is 5. So we just have to write our final answer knowing what c is. So our final answer is that our original function was this, but we found c. C was 5. So it's x plus 2x to the 3/2 plus 5. Again, how can you check your work? I'm not going to go through this process because you guys know how to do this, but take the derivative of this. You should end up with this. And you will. Remember, this is just 3x to the 1/2. Great. Okay, I have another example that looks like this. I think these are the more challenging ones, but they're kind of fun algebraically. So let's do one more and then you have your daily assignment. All right, same problem. Type of problem. All right, the first thing I'm going to do is rewrite f prime. So I haven't done any calculus yet. I'm going to write this as x to the -3rd. Whoa. Instead. That just helps me out. Like in the last problem, I rewrote the square root of x as x to the 1/2. It's just more helpful. Okay, so we need to find the antiderivative first. So the antiderivative of f prime would just be f. We're just working backwards. And actually, what I can also do is write this as x to the 1st. So we're going to use our backwards power rule here because we have x to the n, and neither of those n's is -1. So we're going to use that rule where we do x to the n plus 1, and then we divide by that value. I'm going to do the same thing over here. Now, adding 1 to -3 gives you -2. It does not give you -4. That is subtracting. Just because a number is negative or just because a number is a fraction doesn't mean that the rule is any different. You just have to be more careful. So we're going to use the same rule here. We're going to add 1 to this value. which is -2, and then we're dividing by that value. Great. Then we have a plus c. Okay, let's clean this up a little bit. I can't really clean up this first term. I can, however, say that this will just end up being minus. And instead of writing x to the -2nd, I'm going to write it as x squared in the denominator, because that's what that means. Then plus c. Okay. Again, if you want to make sure you're doing things right so far, I would highly suggest taking the derivative of both of these terms and making sure you get this. This one works. This one works too. Okay, now this is the general antiderivative. If you were asked to find a general antiderivative, you're done. But you're not done, because we got this. So we need to use this piece of information to find c, the particular constant in this case, right? So we know that when we input a 1 for x, we get an output of 6. So we know our output's 6 when our input is 1. Oops. Ugh, that's a squared. All right, plus c. So solving this is just a 1/2. This is minus a 1/2. Love an input of 1. That's super easy. Plus c. Great. So 1/2 minus 1/2 goes away. So we're left with that c is 6. So we can write our final answer. Our particular antiderivative is here, except we can plug in what c is. Cool. There we go. Okay, so we've done a lot of examples. I know this was a lot for one video. We'll have another day to practice a lot of this stuff again. But the biggest thing is just the algebra. Again, that's what's going to hurt you if you're not strong with it. So just be careful. Use your calculator if you need to check stuff. Here's your assignment. Okay, today's daily assignment is finding 4 general antiderivatives. You're going to have plus c's with all of these at the end. Then you're going to have one where you have to find c. These are like the last 2 examples that we just did. This one's not as tricky algebraically as the previous 2, but it's the same idea. So use the first part of the video to find the general antiderivatives if you need to refer back to it, and the table that was provided for you with all the different rules. This is also finding an antiderivative with a plus c, but then using this piece of information to find the particular value of c. Okay, best of luck. Please ask me questions on Zoom if need be, and get this uploaded to Blackboard. Bye, guys.